Welcome back to The Explainer. Today we're popping the hood on DeepSeek-V4 to figure out exactly how it achieves such massive scale without completely collapsing under its own compute weight. If you've been tracking the AI frontier lately, you know that scaling isn't just about throwing thousands of GPUs at a problem anymore. It is about fundamentally rewiring how these models actually think, remember, and optimize.
So, let's dive into the absolute boss-level problem in AI today, processing a 1 million token context window without completely blowing out your memory limits. Now, for some perspective, 1 million tokens is kind of like reading the entire Harry Potter series in a single breath. Traditionally, attention scales quadratically, which means every new token has to look back at every single past token. So at 1 million tokens, the math just explodes. But DeepSeek-V4 attacks this head-on with a totally massive structural redesign.
To see how they actually pull this off, here is our roadmap. We're going to hit the million token challenge, rewiring the foundation, the hybrid attention memory hierarchy, the optimization stack, post-training for agentic behavior, and we'll wrap up with the future of frontier models. Let's get right into it. Starting right at the base, rewiring the foundation with MHC. You see, simply making neural networks deeper introduces some really serious optimization instability. Standard residual networks rely on basic pathways, but at trillion parameter scales, that simple plumbing just starts to break down.
Enter MHC, or Manifold-Constrained Hyper-Connections. Now think of this like a highly regulated, super stable highway system for data. Instead of those unconstrained pathways where signals can basically spiral into a massive traffic jam, MHC projects these signals onto what's known as a Birkhoff polytope. In plain English, it uses incredibly strict mathematical constraints to tightly regulate the flow of information, completely preventing total traffic collapse across those super deep layers. The absolute key takeaway here is that this geometric constraint keeps the feature energy perfectly balanced, no matter how ridiculously deep the model gets. By ensuring every output stream is this perfect mixture of input streams, the network never arbitrarily amplifies the signal. And this stability isn't just a band-aid, right? It's literally baked directly into the geometry of the model itself. Now you might be asking, why does this actually matter for us? Well, this level of systems code design is what makes trillion parameter scaling practically doable without instantly exploding your memory bandwidth. DeepSeek pulls this off with a differentiable sinkhorn projection, fusing the math right at the hardware kernel level, and it only adds a modest 6.7% training overhead. It's honestly an absolute masterclass in balancing pure math with the harsh realities of hardware.
All right, moving to part 2, hybrid attention memory hierarchy. Let's see how this foundation actually builds up into the model's memory system to solve that massive quadratic attention bottleneck we talked about. This perfectly illustrates the complete shift from a monolithic memory model to a specialized, layered system. Instead of forcing one single mechanism to handle all the context, DeepSeek-V4 splits the job up. It's a lot like a tiered city library sorting system, completely dividing the labor into compressed, sparse attention, or CSA, and heavily compressed attention, which is HCA. First up, we have CSA. This handles the really fine-grained, long-range retrieval. Think of it as your highly structured, lightning-fast index. It compresses the history and then uses sparse attention to pull out exactly what it needs. Crucially, it manages to keep these pathways in ultra-efficient FP4 precision using an FP4 lightning indexer, which drastically cuts down on those memory bandwidth constraints.
On the flip side, HCA acts almost like a giant hydraulic press for your data. It just crushes that context down into a tiny latent space, which lets the model perform dense attention over a drastically reduced sequence. When you put CSA and HCA together alongside a heterogeneous cache, they flawlessly manage these different compression ratios. So it isn't just a slight upgrade, it's a completely reimagined memory hierarchy from the ground up.
Okay, part 3, optimization as an architecture. This is where we examine the engine block itself and where optimization stops being an afterthought and becomes a core structural pillar.
You know, the classic Atom optimizer really starts to choke at trillion parameter sparse scales, so they brought in the Muon Optimizer. Muon tackles the gradient noise and routing imbalances that totally plague these massive models. It acts as a structural conditioner, using geometry-aware preconditioning to stabilize the entire learning trajectory of the network. It's a real game changer.
And here is the ultimate payoff for all that hardcore structural engineering, the raw numbers. DeepSeek-V4 Pro is running at just 27% of the inference compute of its predecessor, and it uses a staggering 10% of the KV cache size. And the Flash variant pushes it even further. This right here is what true structural scaling actually looks like in practice.
So what's the big picture here? It's that architecture and optimization are now totally inseparable. They're a single, tightly co-designed object. When you have FP4 quantitation layered deep into pre-training and distributed systems coupled perfectly with the model structure through contextual parallelism and tensor-level checkpointing, software engineering and model scaling just blur together at the frontier. You literally cannot scale one without perfectly designing the other.
That brings us to part 4, post-training for agentic behavior. Let's talk about the brain of DeepSeek-V4, moving from just a passive language model to a highly active agent.
What's really cool is how DeepSeek decouples acquiring a skill from integrating it. Step 1, individual domain experts, say for math or coding, reach local mastery. Think of them as isolated university professors. Then they are optimized using GRPO training, and finally a unified student model learns from all these expert teachers at once through on-policy distillation. Basically, they build the experts first and then forge them together into a single mind. And this leads to an absolutely fascinating trick they call differentiated thinking management. Basically, it's conditional memory management. If the model is just having a casual chat, it discards its past reasoning to keep the context light and super fast. But if it's using tools and acting as a complex agent, it locks in that context to maintain a multi-step trajectory. It intrinsically knows exactly when it needs to remember its own thought process.
The big takeaway for us is that DeepSeek-V4 handles agency through structured decomposition. It's treating tool orchestration, code debugging, and error recovery as literal cognitive skills, optimizing for those long horizon returns. It leverages external tools as a literal extension of its own cognition.
Finally, part 5, the future of frontier models. Let's zoom out a bit. Where's this all actually heading for the broader landscape of AI? When you see this dramatic drop in compute, it proves a massive point. The future of scaling is absolutely no longer just about making one single mechanism bigger. It's about reorganizing primitives. We aren't just blowing up the size of standard transformers anymore, right? We are meticulously designing composite systems that are fundamentally cheaper to run and much, much smarter. But of course, this level of complex systems co-design brings up some huge open questions. I mean, what really are the limits of extreme FP4 quantization? Is this aggressive compression going to subtly degrade complex reasoning over super long distances? And maybe most importantly, how on earth do we audit a system that is this deeply layered? Interpreting heterogeneous networks is going to be incredibly difficult. It really comes down to this tension between structured capability and interpretability. That's the ultimate tightrope that all future models are going to have to walk. As we swap out these simple monolithic layers for these intricately tuned, hyper-specialized components, we are gaining incredible power for sure, but we're also risking the creation of these black boxes that are almost impossible to unpack mechanistically. So will future architectures look less like singular brains and a whole lot more like societies of interacting modules? I'm going to leave you to ponder that exact question as we watch AI scale not through brute force uniformity, but through brilliant structured composition. DeepSeek-V4 gives us an incredibly clear look at a future of specialized memory hierarchies and unified expert systems. Thanks for hanging out for this explainer, and we'll catch you on the next one. Keep questioning the frontier.